Okay, so in the last session, we had a discussion on queues, and we are done with all the different types of queues. So there we have studied what is a linear queue and its implementation. Then we have seen circular queue, then its implementation. Then we have also seen priority queue, then double-ended queue. Okay, so after that, we'll be starting today with our new module, and our new module is linked list. So today we'll be starting with linked list, and before starting with linked list, we need to see and understand what's the difference between a linked list and array. Okay, so here we have the major differences between a linked list and an array. So as you can see here, the first point is that the linked list makes use of dynamic memory allocation, and your arrays makes use of static memory allocation. Now, this we have already discussed in the last few sessions that arrays makes use of static memory allocation, which is done at the time of compilation. And that's why whenever you define an array or whenever you declare an array, you need to specify the size of that array. For example, you are declaring an array of int type, and suppose the name of the array is A. So you will be writing int A, and then in square bracket you need to specify the number of elements you want in the array. So for example, 5 elements you want or 10 elements you want. So accordingly, you would specify the size of an array. And when we specify the size of an array before compilation, so during compilation, that much memory has been allocated to that array, depending upon the type and depending upon the number of elements. So, for example, if the type is say int, and suppose the integer takes 4 bytes, and if you have declared an array of 5 elements of int type, so one element of int type is taking 4 bytes, so 5 elements would be taking 20 bytes. So a 20 bytes block would be created, and that block would be allotted to that array A, and the name of that block would be A. Okay, and this is done at the time of you can say compilation, and that's why it is called static, because it is fixed. Once it is done, you cannot change it. Okay, and then that name of the array A, which is pointing to the starting address of that block, is called as a constant pointer. So even that pointer cannot be changed. You cannot assign any other address to that array name A. Array name A is a constant pointer that you need to always remember. Okay, and if you see on this side, that is linked list side, so the first point says that it uses dynamic memory allocation. So for linked list, the memory allocation is done dynamically. It simply means that memory allocation is not done at the time of compilation. It is done rather at the time of execution, when the program is executing, when a program is running. So the execution of your program starts from the main function. So your program has started executing, has started running, and during its execution, you can allocate a memory. Okay, depending upon your exact requirement. So basically, in fact, you can decide as per your requirement during the execution of a program that how many elements you need or how much bytes you need, and accordingly then you can request for the allocation of that much memory to a system. And this request is done with the help of library functions like malloc. So malloc is one function. Likewise, you have calloc, another function. So these are the library functions which are used to request to the operating system or request to the system that we need this much memory, and if you can allocate this much memory, then please do allocate. Okay, so this is called dynamic memory allocation. Memory allocation is done during the execution of program or during runtime. So whenever you execute, whenever we allot a memory or allocate a memory during the runtime, then it is called dynamic memory allocation. Then the second point says that in arrays, the inserting and deleting elements are difficult. And in linked list, inserting and deleting the elements are easier. What does it mean that if you visualize an array, so in an array, You have first element, then you have second element, then you have third element, then you have fourth, then you have fifth. So, for example, if you want to delete the middle element, so what is expected that the out of five elements, when you delete the middle element, so the lower two elements should be shifted up. Okay. Likewise, if you want to insert an element at the first position and already four elements are being inserted, so you need to shift down all the four elements by one position, then have a free space at the first position, and then insert the element at the first position. So simply it needs shifting of elements from left to right or right to left. Okay, the way you need the insertion or deletion, you need to shift the element, and then this shifting is not easier. It is little difficult and it takes time. Okay, so if you want to delete one element, and suppose the array is of 100 elements, and if you want to delete one element, so it is quite possible that you may need to shift remaining 99 elements by one position. Okay, so that will be taking time. Likewise, if you want to insert something at between or at the first position, then you need to shift down all the elements by one position. Okay, and then the same you need not have to do in linked list. Here we will see that how do we insert element into the list, and then how do we delete the element from the list. Okay, so there is nothing like shifting. You need not have to shift the element from left to right or right to left, as we need to do in the array, because if you recollect the basic definition of the array which we have discussed, is what, that the array is a collection of elements of similar type. Array is a collection of elements of similar type which are always stored consecutively in the memory. This is very important. Which are always stored consecutively in the memory. It means that after first element of the array, you have second element only. There is nothing in between first and second element. Likewise, there is nothing in between second and third element. Likewise, there is nothing in between third and fourth element, and so on. Okay, so that's a very important concept about an array, that all the elements are always consecutively stored into the memory, and because of that consecutive storage, you need to shift the elements whenever you perform any insertion or deletion. And in case of linked list, this is not the constraint. You do not have the elements consecutively in the memory. Okay, the elements can be at different places into the memory. That we'll see when we see the example of linked list. Then the third point, the same point is coming down, that in arrays all the elements are consecutively stored. Okay, in the arrays all the elements are consecutively stored, and for linked list this consecutive storage of elements is not required. Okay, so we do not have any consecutive storage of elements in the linked list. Then in linked list, elements can be accessed sequentially. This is a important point, or you can say a little drawback if you consider it as that into the linked list, that the elements can be accessed only sequentially. You do not have a random access. Whereas in arrays, you can randomly access an element. Now, what do you mean by random access of an element in array? If you have got an array of five elements, so we know that the first element is present at the index value 0, second element is present at the index value 1, third element is present at the index value 2, and so on. So if I want the last element of this array, what I would be writing? Simply I would be writing A in square bracket 4, because 4 is the index value of this last element. So this is called random access. It means that if I want to access the last element, I did not have to access the first, second, third, fourth, and then the fifth element. But in case of English, you need to do that. If you want to access the last element, you will get the address or the location of the last element from the second last. Then the location or address of the second last from the third last, and so on. So you need to start from the first element. First would give you the address of second. Second would give you the address of third. Third would give you the address of fourth. And then the fourth would give you the address of fifth, if I want to access the fifth element. So in linked list, the access of the elements is always sequential. In sequence, one by one, we access the data element. But in array, this is not the case. We access the elements randomly. Okay. So random access is there into arrays. with the help of index value. Always remember, with the help of index value, we can randomly access the array element. Okay. Then the next point is, obviously in arrays, the size is fixed. The size is fixed. Okay. Once you define it, a of 10, and that 10 number is fixed, then later you cannot make it a of 11 or a of 9 or a of 5. Okay. So that array of 10 elements is now fixed. You need to use that only. But in case of linked list, this is not the case. Since a memory is dynamically allocated, then this size is not fixed. And we say that the structure, that is the linked list data structure, can grow and shrink dynamically. The linked list data structure can grow and can shrink dynamically. Okay. The data structure can grow and shrink dynamically. This is the main concept of your linked list. Why? Because it has dynamic memory allocation. Then the last point, array faster, since memory allocation is done during compile time. Since the allocation of the memory in case of arrays is done during the compilation of your code, so you do not have to do this at the runtime. So during runtime, the arrays are faster. Second important thing to make it faster is the random access. You can randomly access the element, so that also makes it faster as compared to linked list. On the other hand, linked list is slower since memory allocation is done during runtime. Now, during execution itself, you are requesting for the memory. You are calling the malloc function. Then the malloc function is returning your memory. It means that this is going to take some time during the runtime, during the execution. And that's why we say that it is slower as compared to arrays. Arrays, static memory allocation, which is done at the time of compilation. So runtime is faster. And in case of linked list, dynamic memory allocation. So memory is allocated during the execution of the program with the help of library function. That's why the execution is little slower as compared to your arrays. Okay. So these are the major differences, or you can say linked list versus arrays kind of stuff. And what all points are important? Memory allocation. In arrays, you have static. In linked list, you have dynamic. Then inserting and deleting the elements in arrays is little difficult. In case of linked list, it is called simpler. Then in arrays, all the elements are stored consecutively. In linked list, the elements are not stored consecutively. That is not a constraint. Then in arrays, elements can be accessed randomly. This is very important with the help of index. With the help of index, in arrays, you can access the elements randomly. In case of linked list, there is no random access. You need to access the element sequentially. Then in arrays, the size is fixed because it is declared at the time of compilation, and the static memory allocation is done at the time of compilation. So the size is fixed. You cannot change it. In case of linked list, the size is not fixed. It can grow or it can shrink dynamically. So there is no memory wastage, you can say. And you can go for memory allocation on fly. So as and when required, you can go for memory allocation. Then when it is not required, you can free the memory. So it is all done dynamically. Okay. So your structure grows and shrinks dynamically. Then arrays, it is faster since the memory allocation is done at the time of compilation, and it gives you random access also. In case of linked list, it is slower, little slower as compared to arrays because the memory allocation is done during runtime. So these are the major differences between linked list and arrays. And once we are done with these major differences, once we come to know what are the basic differences between arrays and linked list, then we can now start with what do you mean by linked list, and how we can go with the different types of linked list and how we can have it practically. Let me close this. Okay, so PowerPoint presentation just to understand the basic concept of linked list. And I hope that you will be understanding it quite clearly. So if you remember, then we have already seen that a data structure can be categorized into two type or two category. One is your linear data structure, another one is your non-linear data structure. Then under your linear data structures, you have arrays, then you have stack, then you have queues, and then the most important one is your linked list. So basically, your linked list falls under linear data structure. Then in the non-linear data structure, you have trees, and then you have graphs. Okay. So the first thing is what? A linked list is a linear data structure. Okay. So it is a linear data structure which is a collection of something called as nodes, collection of nodes, and these nodes are interconnected. These nodes are interconnected. Okay, and that's why it is called as linked list. List is what? Collection. List is basically a collection of group of elements. Okay. Now, in this case of linked list, instead of calling them as simple elements, we call them as nodes. We'll see what do you mean by nodes. So it's a collection of nodes. A list is a collection of nodes, and then these nodes are interconnected. Now, since these nodes are interconnected, so we call them linked lists. Okay, and then the entire structure is called as linked list. Let's see. Now, to understand the basic concept of linked list or the fundamentals of linked list, we need to always first compare it with arrays. That's what we have already done. Now, if you see this example, so in this example, how many elements we have? We have total 5 elements of the array. Before this, let me do one thing. I need to understand your questions also. So, what I would be doing, I am stopping this presentation. Let me present a window. Okay. Okay, fine. So this is an example of array. So you have total 5 elements into this array, and you just imagine that you have declared an array of integer. So all the elements into this array are of integer type. So just take an example, int a, and then in square brackets you have written 5. So this is a memory representation of that array, int a, and then in square bracket 5. Okay. Now, once we have this setup in the memory for an array, and we know that an array is a collection of elements of similar data type, and all the elements are always stored consecutively. So that's why the first element is 10, the second element is 20, 30, 40, and 50. And all these elements are stored consecutively. Now, what does it mean? Uh, on this left-hand side, what we can see is the index number of the element. So the first element is having an index value 0. Then the second element is having index value 1. Then we have index value 2. Then we have index value 3. Then we have index value 4. Okay. So here in this array A of 5, the first element A of 0 is 10, then A of 1 is 20, A of 2 is 30, A of 3 is 40, and A of 4 is 50. Okay? Now, on the left hand side of this array, what we have written are called the indices or the index number of the elements. Okay? Now, I also want to write the address of these elements on its right hand side. And let's suppose that the address starts from the location 8000H. H stands for hexadecimal. So at 8000H, the first element is stored of this array. Okay. Or you can say that this array starts from memory location 8000H. I repeat, this array starts from memory location 8000H. Fine. So you have the first element, that is 10, at a memory location 8000H. Now suppose that one integer takes 4 bytes. One integer takes 4 bytes. So what would be the, or what should be the address of the second element 20? Please tell me what should be the address of the second element 20? You can post your answer into the chat box. Yes, I am getting the answer. Few students are saying it is 8004. Absolutely right. The address would be 8004. Okay. Why? Because at 8000, 8001, 8002, and 8003, 4 bytes. I repeat, 8001, 8002, 8003, and 8004. Okay. So at these 4 bytes, your first integer, your first element, that is 10, would be stored. Okay. Now, how that 10 would be stored, that's a different story. We called it IEEE standards. So as per those standards, the numbers are stored or the values are stored into the memory. We don't have to get into that detail, but what we need to now remember, that we have assumed that one integer is taking 4 bytes, and my first integer is stored at 8000H. So my second integer, which is consecutively stored, would be definitely stored at 8004H. Likewise, our third integer would be stored at, our third element would be stored at 8008. Perfect. At 8008. Then the fourth element would be stored at, which address? 8016, 8012, 8012, 8012. Let me remind you, I'm writing H. H means hexadecimal. One student has written 8000B. Perfect. The next element is stored at 8000B. Why? Because this is hexadecimal number system. After 9, you do not have 10. After 9, you do not have 10. Decimal number system, DEC. DEC means 10 possibilities. That's why when we start from 0, we go up to 9. 10 possibilities. We start from 0 and we go up to 9. So total 10 possibilities are done. So after these 10 possibilities, you again have combination 1 0, then 1 1, then 1 2, 1 3, and so on. Okay. But this is a number system where you have hexadecimal number system. 16 possibilities. Hex means 16. So you have 16 distinct possibilities. I repeat, 16 distinct or indivisible possibilities. So 0 to 9, 10 possibilities. After 9, you should not have repetition. So because here you need to have 16 possibilities. So after 9, that is 10 possibilities, you have A, then you have B, then C, then D, then E, and then F. So 16 possibilities are done. That's why you do not have E after F. Sorry, G after F. You are going only up to F in hexadecimal number system. Okay. So your after 8008, after 8 you have 9, and then after 9 at 8008, 8008, 8009, And then after 8009, you do not have 8010, you have 8000A. So 8000A, then 8000B. Okay. So your next would be 8000B, and likewise, your next would be 8000F, not G. You do not have, you do not have G into the hexadecimal number system. So after 8000F, you have 8010. Then comes the repetition. Okay. So 8010, 8011, 8012, and so on. So please see it very carefully. Try to understand it very carefully. This is how an array is represented in the memory. Whatever you have on the left hand side, that is 0, 1, 2, 3, 4, that is not a part of your memory. That is basically for our understanding. So in the memory, you have these values 10, 20, 30, 40, 50, that's all. And 10 is stored at the address 8000H. And if int is taking 4 bytes, so 20 would be definitely stored at 8004, then 30 would be at 8008, and so on. Okay, so this is how an array is represented in the memory. I hope that the array representation in memory should be clear to all. This is how array is stored into the memory. Now, I should proceed with linked list, but before that, I would be asking you, in one of the programs, in the comment part, when we were talking about the code, and if I am not wrong, it was the infix to postfix conversion, where I said you that you can access the array elements or the string elements by writing say a of I. So that a of I, a in square bracket I, where a is the name of the array and I is having the index value. The same can be written as I in square bracket a. And I ask you people to check it practically, whether that can be done or not. Okay. So if a is the name of an array, I is an index position or the index value. So you can write a in square bracket I. Generally, we write it like this. But can you write ai and then in square bracket a? Or what I mean to say that if you are writing a in square bracket 0, so can you write 0 then in square bracket a? The way you can write a of 4, a in square bracket 4. So that will give you the value 50 or the data element 50, a in square bracket 4. So can you write 4 and then in square bracket a? Yes, you can perfectly write that. Why you can write that? Because there basically the indexing is for us, not for the system. What the system understands? The system understands the address. Okay. So basically when you write a in square bracket I, so you are writing something like star, then in parentheses a plus I. I repeat, star, and then in parentheses a plus I. Okay. So if you write a or a square bracket I, that is translated, that is converted into this statement by your compiler. Star in parentheses a plus I. So if you write I in square bracket a, so that is also converted or translated by your compiler into a statement star in parentheses I plus a. So now, whether it is a plus I or I plus a, the answer is same. It is as good as x plus y or y plus x, one and the same thing. So likewise, whether in that parenthesis you are writing a plus I or I plus a, it is one and the same thing. And that's why a in square bracket I is similar to I in square bracket a. It doesn't matter what's an array name or what's an index variable. You can write in either way because it is getting translated into a single same statement. Star in parentheses a plus I. Okay. Or you can say star in parentheses I plus a, one and the same thing. Okay. So we are not getting into the detail of that. So this is how array is represented in a memory. Now in the same line, if I want to see how does a linked list is represented in the memory. So the first thing about linked list, what we have discussed is a linked list is a linear data structure which is a collection of nodes, and these nodes are interconnected. So first of all, we need to understand, yeah, what do you mean by node? Because this node is a basic thing in a linked list. Okay, it is a fundamental of linked list. So we need to understand what do you mean by node. Once we understand a node, then we understand the rest of the thing. So basically, when we think about any data structure, so we say that basically a data structure is something or container in which we are going to put our data. We are going to organize our data. Okay. So in a node, a data is going to be an important part, no doubt about it. When I say a node, a collection of nodes, a list is a collection of nodes, and these nodes are interconnected. So the first thing is I need to understand what do you mean by node. So in a node, there is one part, and that part is called as a data part. So basically, my node is going to be a two-part thing. One part is my data part, and another part is something called as a link part. Okay. So one part is my data part, another part is a link part. So when these two different parts are joined together, then this collection, this complete block is called as a node. Okay. So now we can say that in a single node you have two things. One is your data part, another is your link part. Okay. Our first part is the data part, second part is the link part. Now inside this data part you can store whatever you want. The way we can have array of int, array of float, array of character, array of double, array of structure, okay, array of pointers. Then those pointers can be pointer to int, pointer to float, pointer to character, pointer to function as per our requirement. In the same line, in this data part, you can store whatever you want. You can store simple integer, you can store simple float, you can store simple character, you can store string, you can store structure, you can store function, address of a function, you can store address of a program, whatever you want. Okay. So this data part basically resemble your data. It represents your data. Your data can be anything as per your requirement. I repeat, your data can be anything as per your requirement. Okay. So in your node, you are going to have two parts or two things. One is the data part, second is the link part. Your data part, depending upon your requirement, can be anything. For illustration purpose, for explanation purpose, in most of the books, in most of the references, this data part is given as an integer value. The way we have all the integers in our array right now. So if you see our array, so what we have 10, 20, 30, 40, 50. So basically for understanding purpose, basically for explanation purpose, for illustration purpose, we go with a very simple example. So that's why we generally prefer to use the integer values as a data. But I say you again, it is absolutely upon your requirement, depending upon your requirement, your program requirement. Whatever you want to store, you can store into the data part. Okay. So this data part can store or will be storing your data, which can be simple integer or which can be anything else. Second is the link part. Now this link part is basically going to store the address of another node, because what we have seen about linked list, a linked list is a linear data structure which is a collection of nodes, and these nodes are interconnected. Okay, so there should be some way by which nodes are connected to each other. They are linked to each other. Okay, so this part, the second part of your node, which is called as a link, will be connecting to another node, or will be having something which will tell you, okay, where is the next node? Where is the next node? Now, can you tell me what would be the content of this link? As I said you, the content of the data part is what? Depending upon our application, depending upon our requirement. It can be integer, it can be float, it can be anything. For explanation purpose, we go with integer values. Okay, so it can be 10, it can be 20, it can be 1, 2, 3, whatever we want to store. Now, can you tell me what will be the link part, or what will be stored into the link part? I got one answer. Alfia says pointer. It is going to be a pointer. Any other answer? Any other student want to answer this? What will be there inside this link part? Address of data. Okay, good answer. First answer was also good. Pointer. Second address. Second answer is address. Address of a data. Address of another data. Okay, more clarification. Address of another node. Good, very good, mashallah. So we are reaching to the answer step by step. The first answer was pointer. Yes, it's a pointer. Second answer, it was it's an address of a data. Yes, it's an address of a data. Then came the next answer, address of another data. Yes, it is an address of another data. Then came another answer, address of another node. Perfect. It's an address of another node. Okay. So basically, it contains the address of another node. Because what we have seen, a linked list is a linear data structure, which is a collection of nodes which are interconnected. So these nodes are interconnected. So one node should have the address of another node, wherever it is. It is before this node, or it is after this node, wherever it is. It can be anywhere in the memory, because these nodes or these elements are not consecutively stored, as we have the case in arrays. In arrays, all the data elements are consecutively stored, but in list, these nodes are not consecutively stored. They can be anywhere in the memory. And that's why we need to have a pointer. That's why we need to have the address of second node into the first node, and then the address of third node into the second node, and then the address of fourth node into the third node, and so on. Okay. So from my first node, I can go to my second node. From my second node, I can go to my third node. From third node, I can go to my fourth node, and so on. And if this is my last node, then the link part should have a value which indicates that this node is the last node. What should be that? Any guess? For example, if this node is not pointing to any other node, so what should be the link value? Absolutely right. The link value should be null. Okay. And here we have the example of a node, a single example, single node. Okay. So for example, the data is 10, as we have in the case of the first element of our array, the data value is 10. So here also we have one node, and that node is having a value 10, or the data part as 10. And if I have only one node in my list, that node is not pointing to any other node. So the link part of that node would be null. Okay. So this is one node, and the data part of the node is a value that is 10. And then the link part of this node is null, because this node is not pointing to any other node. Okay. So this is how a linked list is represented in a memory. Now, this is my first node, or this is my one node. Now, what if I want to add more node into my list? I want to add one more node. So in that case, what would be happening, or how we would be going? Let's see an example for this. So I'm going to create the first node. When I create the first node, into the data part, I would be putting my data. Then into my link part, I would be starting with null. because this is my first and the only node, and this node is itself present at memory location, and the address of that memory location is 9000H. Please understand it, try to understand it very clearly. What we are saying that we have one node, a node has been created, dynamic memory allocation. So malloc has been done. We have called malloc function. We have asked for a memory. A memory has been allotted to us, and that block which has been allocated to us, that block is present at the memory location 9000H. That block is present at the memory location 9000H. Inside that block, you have two parts. Inside that block, you have two parts. The first part is the data part where this 10 is stored, and the second part is the link part where we are storing null. Because right now, this is the only node with us. This node, I repeat, this node is present at the memory location 9000H. The first part, that is the data part of this node, is having a value 10. And the second part, that is the link part of this node, is having a value null. Okay, so there is one node in the memory. That node is present at the memory location 9000H. The first part of the node is having a value 10. The second part of the node is having a value null. Now I create one more node. I want to insert a node into this list, this linked list. So I would be creating one more node. So first the data part, I'm putting 20 into that. Second, the link part. Then I put null into this link part. And then this node has been created at a memory location 8050. See here carefully. The first node is created at or present at the memory location 9000H. The second node is present at the location 8050H, 8050H. Okay, they are not at all in sequence. The first node is at 9000H. If this is my RAM, my addresses are starting from top and it is going up to bottom. So the 9000H is somewhere in between. So this 8050H is before 9000H. Okay, so my first node is at 9000H and my second node is before that node. So it is absolutely as per the availability of the memory. So when we call the malloc function, depending upon the availability of the memory, the malloc function will return us the address of the block. Okay, so the second block or the second node is present at the memory location 8050H or 8050H. Its data part is 20. Its link part is null. Now I want to link these two nodes. So I want to make the data element 20 node as the second node and 10 as the first node. 10 is my first node for sure because that was the first node created. This is the newly created node at 8050 and I want to link this node to the to my first node. So what I want to make or what I want to do, that the link part of the first node should be pointing to my second node. So that I will be doing by removing this null from the link of the first node and making it 8050. So the moment I write the address of the second node into the link part of the first node, I repeat, the moment I write the address of the second node into the link part of the first node, what I do, basically I make my first node to point to the second node. What we are doing, we are making our first node to point to the second node. Okay, so now our first node has started pointing to the second node, and we say that these two nodes are interlinked. We say that the two nodes are interlinked. Okay, now take one more step ahead. I want to add or insert one more node into this list. So what we will be doing? We will be allocating a memory. A data part would be created. Suppose it is 30. The link part would be created. By default, initially it would be null, safe programming. Then this is allocated at a address 7000H. Okay. So now this node, the third node, which is having a value 30, is present at the memory location 7000H. Is present at the memory location 7000H. And I want this node to become the third node of my list. So basically what we will be doing, we will be going to the second node or the last node of our list, which is now 20, having a value 20. And then we need to make the link part of this node. So remove the null from that. And I need to make this link part point to the third node. And how we'll be doing that? By assigning the address of the third node, that is 7000H, into this link. Okay. So this link should become 7000H. The moment this link becomes 7000H, it starts pointing to the third node. Okay. And now our list is ready with 3 nodes. The first node is having a value 10. It is pointing to my second node, which is having a value 20. It is pointing to my third node, which is having a value 30, or which is having a data as 30. So the first node data is 10, second node data is 20, and third node data is 30. And this is how it would be represented inside a memory. This is very important, very important. Please understand it very carefully. Okay. I have created this presentation basically to clear the concept of how the memory, how the linked list is represented in a memory. Once you understand this representation, it means that you are understanding the fundamentals of linked list very carefully or very thoroughly, and then we can easily understand the different types of list, the different operations on linked list, and we can easily perform the different operations. Okay, so you need to understand it very clearly. I take the things back. I want to explain you the concepts again. So this is our first node. Our first node has been created. The data part is 10. Okay. The link part is null. And then the first node is present at 9000H. So at memory 9000H in a RAM at a location 9000H, you have one block or one node. The first part of the node is 10, the data part. The second part of the node is null. Okay. Then I want to insert a new node into this list. This is my list with only one node. Okay. And generally, the first node is pointed by a pointer called head. So head is a pointer or your list which always points to the first node of the list. So this node would be pointed by head. Head is going to be a pointer which will give you the head of your list. That's why the name is head. So it will give you the first node of your list, or it will give you the head of your list. Now, can you tell me what should be the content of that head pointer? Come on, fast. The answer is in front of you. What would be the content of that head pointer? The head pointer would be pointing to this node, the first node of your list. So what would be the content of the head pointer? Come on, fast. Post your answer into the chat box. Address of first node. So what is the address of first node? I'm asking you the value, 9000H, exactly. So the content of the head pointer would be 9000H because the address of this node is 9000H. Okay. Then we want to insert one more node into the list. So what we'll be doing, we'll be allocating a memory. Okay. A block would be created, a node would be created. We'll put a data into that data part 20. Then into the link part, we'll be putting null initially, and this node is created or has been allocated or is present at the memory location 8050, 8050H. When I want to insert this node, a newly created node into my linked list, which is pointed by head, what I will be doing, I will be going to the last node of my list. Now, since there is only one node, so that node itself is the last node. Then I will access the link part of that last node. I will remove the null from that last node, and then I will put the address of this new node into the link part of that last node. So this 8050 will come there. The moment 8050 comes there, it starts pointing to this node. And now we have two nodes into our linked list. The first node is 9000H, which is pointed by the head pointer. So the moment I access head, I access the first node. After getting the data of the first node or whatever operation I want to perform onto the first node, from the link part of the first node, I go to the second node. Then I access the second node. Okay, so I get the data of the second node, that is 20. Now I want to insert one more node into my list, which is pointed by the head pointer. So for that, what I will be doing, first I will be creating a node with the help of malloc function. I will be putting a data into the data part. I will be putting a null into the link part, and this is present at a memory location 7000H. So what I need to do, I need to traverse my list. Traversing a list is nothing but starting from the first node and going to the last node. From the first node, you will be going to the second. From second, you will be going to the third, and so on. So with the help of head pointer, I will get the address of the first node, that is 9000H. So we'll go to the first node. From first node, we will get the address of second node, that is 8050H. Inside your first node, you have the address of the second node. So you'll go to the second node. From the second node, we'll go to the next node. Now inside the second node, which is present at 8050H, the data is 20 and the link part is null. So with the help of this null value, we come to know that this is the last node of our list. So now what we need to do, we need to attach the new node, which is present at 7000H, to this last node. How we'll be doing that? We'll remove the null from the link part, and we'll make this link to point to the new node by inserting or by assigning the address of the new node to this link part. So the 7000H would come here. Okay. The moment 7000H is inserted, is assigned to the link part of the last node, then this node or the link part of this node starts pointing to the new node. And now we say that the new node is the last node of my linked list. Okay. So now into our linked list, we have three nodes. The first node pointed by the head pointer is having a data value as 10. Then the second node is pointed by the link part of the first node, which is having a value 20. Then the third node pointed by the link part of the second node, and this third node is having a value 30. And then this third node is the last node because it is pointing to null. Okay. So this is how your linked list is represented in the memory. And this linked list, which we are seeing right now, is called as singly linked list. I repeat, this linked list is called as singly linked list. Okay. So since you have single pointer in each and every node, you have single pointer. That's why it is called singly linked list. So first node will give you the address of the second node. Second node will give you the address of the third node. Third node will give you the address of the fourth node, and so on. And then the last node will be having a null value. So that indicates that it's a last node. And this type of list is called singly, S-I-N-G-L-Y, singly linked list. Singly linked list. Okay. So that is your singly linked list. And this picture is a complete picture of a representation of an array in memory and representation of a linked list in memory. And from this picture itself, if you recollect all the differences between array and linked list, so I'm sure that from this picture itself, you can recollect all the differences. You can talk about all the differences. Okay. So this is the final picture and the fundamentals of your list. Now, the question can be that once we know that theoretically we are understanding that the important part of a list is a node, then we keep on creating the node and then we make them point to each other with the help of addresses. And this is how a list is created, then the list is expanded, then the list is uh, shrunk. And if you remember one of the points of linked list, so we said that linked list can dynamically grow and shrink, can dynamically grow and shrink. So if I delete the last node from this list, okay, so this is how the last node is deleted. So earlier you had three nodes into a list. Now you have only two nodes. So this is shrinking. Okay, dynamically shrinking. Okay, I want to delete one more node from this. So I delink it and I free this node. Done. So one more element is deleted from my list and it is dynamically shrinking. Are you getting it? Now I have only one node. I want to grow it dynamically. Again, I will be going for malloc. I will be creating a node. I will be getting all the addresses linked properly. And now the first node is linked to the second node. So my list is now from one node, it has got two nodes. So it has grown dynamically. It is growing dynamically. I want to add one more. I can add one more node into this list. I can link it and done. So the third node is now the part of my list. And all these things are getting done dynamically during the execution of my program. So we can have options in our program. You can insert a node, you can delete a node, you can find a node, and so on. So your structure is dynamically growing and it is dynamically shrinking. Okay. And this is done because it makes use of library functions malloc and free. So with the help of malloc, we create a new node, and with the help of free, we free the memory or we delete the node. Okay. So your structure dynamically grows and shrinks, grows and shrinks. Any query into this? Because this is very important. If this is done, then we can move ahead. We can move to the next part. Any query into this, please? You can post a query or you can just unmute your mic. Then we can talk about it. Because these basics are important. When these basics are done, we can easily understand the different operations on linked list. We can easily practically understand. If there is no query, so now we can move to the practical part, that practically how the node would be created. Now here, just by removing a link, the next node is deleted. You need to remove a link and then you need to free that node. When you free a node, then only whatever memory you have allocated, you were using, you are freeing that memory. So with the help of that, we say that it shrinks dynamically. Okay. So yes, we just delink it, we remove the link, and then that free node is freed with the help of free memory function, free library function. We free the memory which has been allocated with the help of malloc function. Okay, so that way you'll be freeing up the space, and that way we delete the node. So now the question is practically how you'll be creating the node. You have the node with you, which has the two parts, the data part and the link part. Okay, so practically how to create this node. In our program, I want to create a node. How I will be creating a node? Yes, any idea? Please post your guesses or post your ideas. Okay, so one student is saying with the help of structure, another one is also saying structure. Yes, structure. Absolutely right. With the help of structure, we'll be doing this. Now, let me stop this presentation because we want to see other things also at the same time. So what I will be doing, I will be again starting my presentation where I will be sharing my entire screen so that I can show you other apps also. Okay, so screen is now visible. Fine. Okay, so we are back to the same slide. Uh, Now we are talking about that node, node which is having a data part and also the link part. So how to practically create this node? Okay. Now one student has said that with the help of structure we can do that. So yes, with the help of structure we can do that, and let's do that. Let us start it very plain, simple. So I go for the new file. I think this is our session 17. Let me call it session 17.c. Okay, and here we are talking about link list. So a link list is a linear data structure. A link list is a linear data structure which is a collection of nodes interconnected. Let me simply call it interconnected or interconnected nodes. Okay, so link list is a linear data structure which is a collection of interconnected nodes. We are simplifying it. Right. Then now uh, let me see if I can capture this and put this there. It will be. You just keep this in your mind that we are visualizing this and this we need to put in there. This we need to practically implement. Okay. So a node, as you were saying, node can be created. Node has two parts. Let me write. Node has two parts. One is your data part, and another is your link part. Okay. It has got two parts, data and link part. And how to implement it? So I can say that node can be implemented. Node can be implemented. A node can be programmatically done using structure. So can be implemented using structure. Okay. So how to do that? So in our code, we can have a structure, and let me call this structure as node. Okay. And we are going to have two parts into this data part, and second is my link part. Okay. So one is the data part and second is the link part, as we have studied. Now this data, for understanding purpose, as I said you, I am saying you again, you can store whatever you want. So this data can be a structure, this data can be an array, this can be pointer. This is absolutely as per our requirement. But as we are seeing into the example, most often the data part is integer, just to make our examples easier to understand and nothing else. So our data is an integer. So here we'll be making this data as a integer type data member. Okay. So this data becomes integer. And if we see the link part, so what we are expecting into the link part? If you see the example at the bottom, okay. So this example, sorry, make use of a later point. So if you see this example, this I want to highlight here. Oh, sorry, into this example, the link part. What is this link? What we are storing into the link part? Come on, you need to tell me. This is important. Address. Absolutely. Address, address, address. All should be answering me address. So we are storing the address. Now, can you tell me address of what? Run fast. Address of what? Address of what? This 8050, which I am highlighting here. Let me change my highlight. Okay. I am asking you, what is this? This is an address. This 8050 is an address of what? Can you please post your answer again? I missed seeing your answer. Address of next node, address of next node. Absolutely right. It is an address of next node. Or simply, I can generalize it that it is an address of a node. What it is? It is an address of a node. And so here I understand that it is an address of a node, and address is nothing. To hold an address, what do we need? To hold an address, what do we need? To hold an address, we need a pointer, right? So this link is going to be a pointer. So I put a star, okay? And it is holding an address of a node. It is holding an address of a node. So if you want to hold an address of a pointer, so your pointer would be pointer to, if you want to hold a address of an integer, so your pointer would be a pointer to integer. If you want to hold address of a float, then you are going to have a pointer to float. If you want to hold an address to a character, then you will be having a pointer to character, and so on. Here I want to hold an address of a node. So it should be a pointer to node. Okay. And this node is nothing but a structure. This node is nothing but a structure. Okay. So what we are going to have here, a pointer to structure. So basically here we'll be having a pointer to a same structure node, a pointer to a same structure node. See it carefully. What you are having, you are having a pointer to same structure node. Okay. Now someone is asking that whether it is a nested structure. No, it is not nested structure. This is a structure which is called as a self-referen- self-referential structure. This is not nested structure, but it is called as self-referential structure. Why? Because it refers to self, or it has the potential or the capacity or capability of referring to itself. Okay. Why? Because it has got a pointer to itself. Pointer to itself. The structure name is struct node. The structure name is struct node. Okay, you can see here. Sorry, struct node, and here you are having a pointer inside the structure which is pointing to itself. A pointer to struct node. Pointer to struct node. Okay, so it is called self-referential structure. And when you have a pointer which is of type struct node, then only it can point to another node. Then only it can point to another node. And then only we can say that this address is an address of another node. If you see carefully, 8050, please see carefully, 8050 is not an address of this first part. It is an address of this entire node, of this entire node. This node, this entire node is having the address of 8050H. This entire node is having the address 8050H. And then this 8050, then this 8050 is put into this link part. So basically this link is having the address of the entire node, this entire node. Okay, not only this 20. This 20 is just one part of this entire node. This is my entire node. This is the entire node, and this entire node is present at the address 8050. Okay, and this 8050 we are putting into this link. So basically this link should be something which can point to an entire node. Okay, and that's why this link must be a pointer to the entire node, and your entire node is basically a structure, struct node, and that's why this link should be a pointer to structure node. Your link should be pointer to structure node. The moment your structure or any structure has a pointer to itself, it is called self-referential structure. It is called self-referential structure, and linked list can only be implemented with the help of self-referential structure. You need to have self-referential structure to implement a linked list, because your linked list is a collection of interconnected nodes, and to have interconnected nodes you need to have a self-referential structure. To have interconnected nodes you need to have a self-referential structure, and this is our self-referential structure, which has got two parts. The first part is the data part. Okay, this is my first part. a data part where we are storing a integer type of data. That's why the type is int. And second part is the link part, which is a pointer to the next node, which is a pointer to the next node. Node. It is a pointer to node. That's why this link is a pointer to structure node. Link is a pointer to struct node. Okay. Generally, conventionally, traditionally, this data member, the next part of the node is called as next because it always points to the next node, and that's why we name it as next. Okay, so I'm renaming it. Instead of link, I'm calling it next. So for theory purpose, you can call the second part as link, but practically it is more suited to call it next. It is more suited to call it next, and that's why we name it as next. Okay, because it always points to the next node. That's why the pointer is called as next, and this makes up the structure for the node. This makes up a structure for a node. First is the data part, second is the link part. The data part is called as data. Depending upon what kind of data you are storing, it will be having data type. So here we are storing integer, so it becomes int data. The second part is the link part. We are calling it as next, and it will be holding the address of our next node. That's why it is a pointer to struct node. What it is? It is a pointer to struct node. Okay, so this is how a structure is created to have a node. Any query into this? If you have any query, please put your query into the chat box. We can discuss on that. Else we can start with our implementation. No query? So can I assume what is the size of a node? Good query. What should be the size of this node? Uh, Before that, before coming to the size, let me once again uh, explain this structure. A self-referential structure is a structure which can refer to itself. That's why it is called self-referential. How it can refer? It can refer with the help of pointer. So in short, whenever inside your structure you have a pointer to itself. C programming gives you this liberty. You can declare the structure which can have a pointer to itself. And because of this liberty only, we are in a position to implement the linked list. Okay? So whenever your structure can have one of the data members as a pointer to itself, then such a structure is called self-referential structure. Okay. So in this structure, we can see here itself, there is a pointer which is of same type. The structure is struct a node, and here we have a pointer as one of the data member of this structure, which is pointing to itself. Okay. And this is possible. C allows you doing this. And because of this possibility only, we can have self-referential structure. And once we have the self-referential structure, then only we can think of linked list. Because for a linked list, you need to have interconnection. You need to have a capability of one node to point to another node. So when your one node has the capability to point to another node, then only you can visualize a linked list. Then only you can implement the linked list. Okay. So what you need to have into this block is a two-part block, or this node. This node is a two-part node, a data part and a link part. So this link part should have a potential of pointing to another node, and that node will be of same type node. Okay, that node again will be having two parts. One is the data part, then a link part. Okay, so this link part should be pointing to this entire node. So this link is nothing but a pointer to itself of a same type. Pointer to a same type. Pointer to itself, I mean to say pointer to a same type. Okay, now since this is a pointer to a node, that's why this can hold an address of another node. Since this link is a pointer to a node, structure node, then only it can point to another node, the entire node. Okay, and that's why here we have a pointer to a same structure node. Okay, and then only it will be in a position to point to another node, and then only your one node can be linked to another node can be linked to another node, and so on. And then only we have interconnected nodes, and then only we can implement a linked list. Okay, so that is your self-referential structure. Now the question is, what is the size of this structure? Can you tell me what is the size of this structure node? Addition of the sizes of all the data members. The first data member is your data of int type. So if one integer takes 4 bytes, so this data would be taking how many bytes? 4 bytes. If int takes 4 bytes, then this data would take how many bytes? 4 bytes. Okay. Then the next is your pointer. Now this, as the requirement of integer varies from system to system or architecture to architecture, likewise the pointer memory requirement also varies from system to system. On some system it takes 8 bytes, on some system it takes 4 bytes. This is a pointer. Always remember, pointer will be holding what? It will be always holding an address. Okay? Pointer will be always holding an address. Now, the address is an address. It's an address of a block. It's an address of a block like 8000, 9000, 8010, 8050. Okay, you can have anything over there, but the address is an address. So if you say pointer, so pointer will be always having a memory space which can hold an address. And if I say a pointer takes 4 bytes or 8 bytes, we can assume something. And if you want to check that on your system how much it takes, so you can make use of a size of operator. So size of is a function, library function, which returns you the size of whatever you provide, int, then pointer, whatever. So if this also takes 4 bytes, suppose, so integer is taking 4 bytes and this pointer is also taking 4 bytes, so your entire structure would take how many bytes? 8 bytes. It is as simple as that. So your structure, so your node would be taking 8 bytes. Okay. So this way you can easily compute, or you can simply find the size of your structure node with the help of size of operator. Okay. So this structure is done, and I want to simply create. Instead of going for different functions, let me inside my main do some basic stuff. Finally, I would be returning 0, indicating successful execution. And before that, we need to do something. Let me have my head pointer of structure node. So my head pointer and initially it would be set to null. So I say equals null. Okay. Or later I can simply declare my pointer here as a head pointer, and later in my program I can set it to null. So my head is null, so my linked list is empty, and then I can simply create to create what I need to do. As I said you, I need to make use of a malloc function. So what we'll be doing, we'll be calling a malloc function. I'm I'm always trying to come back. So what I mean to say, we can start from a basic and then we can come back to advanced level. So instead of giving you the entire bigger statement, we'll start from the root part of the statement. We'll start from the smallest part of the statement, then we'll go back. Okay, then finally we'll make up the entire statement. So I'm going to call my malloc function, and to the malloc function, what we need to specify the memory, how much memory we want. So we want a memory equivalent to the size of our structure, equivalent to the size of our structure. Because what we want to create our node. Okay, we want to create this node. So for creating a node, we will be making it of a malloc function, and to the malloc function, we need to specify the size, that how much memory we want. So we want the size of our node, memory, which is equivalent to the size of our node. Okay, so I want to go for the size of operator because I do not know the size of my structure. So we want to do a safe programming. So we'll be making it of size of, and how much memory we want, size of my struct node. Okay. So I want the memory which is equaling to the size of my structure node. And the malloc function on successful allocation, it will return us a pointer to this block, okay, or this node. So it will return us address of this node, and that address would be by default a void type. So I need to typecast it, and since it is an address of my node, so it will be typecasted to a pointer of struct node. So struct node star, okay, struct node star, typecasted to this, and this we need to get returned into one pointer, and let me call it as p, simple. Okay, so I'm saying p equals to struct node star malloc in parentheses size of struct node. Okay, this is a final statement, and this p should be a pointer to my struct node. So comma star p. Okay, if this is successfully done, how do you know that whether it is successfully done or not? If p, it means if p is not null. So if p, or let me write for simplicity of understanding, if p is not null, it means that memory has been allocated. Okay, and we can do our work into this because the memory has been allocated. Else, the memory is not allocated, and in this else part, I would be simply saying printf not enough memory. Due to some reason, memory is not allotted to us, so we can say not enough memory. Okay, so this goes into the else part, and into this if this is means this is true, memory has been allocated, so p is not null, p is having the address of that block, so I am allocated with the memory. P is a pointer, so pointer name, and since it is a pointer to structure, so arrow operator, and then I would be writing the data, whatever data I want to put into it. So I want to put 10. So I would be saying 10, then P, and then the next, that is the link part, equals to, initially I want to start with null. So I would be saying null. Okay. So now one node has been created, and into the data part we are putting 10, and into the next part we are putting null. Okay. And since this is my first node, so I want my head pointer to point to this node. So I would be simply saying head equals to P. So the moment I say is head equals to P, it means that my head has started pointing to this node, which is the first node, that is P. Okay. So this is how simple we have created one node. And if I want to add up one more node into this, that also I can do. And then we can traverse the list, so we can display the different elements of the list, so that we can do all the stuff. But we don't want to do it in this way. We don't want to start the life of our program from the main, and we don't want to do everything inside the main. And we'll be going with generalized programming, or the, I mean to say, modular programming. So in that modular approach, we'll be having different functions doing different tasks. So if I want to insert a node into my list, I should have one function to insert a node. I want to delete a node, I should have another function to delete a node, and so on. There's a request to repeat the malloc part. So let me do that. This is a library function, malloc, which stands for memory allocation. Malloc. M for memory, ALLOC, alloc for allocation, so memory allocation. So this is a library function to allocate a memory during the execution of a program. So when you call this function, you need to specify that how much memory you want, 1 byte, 2 byte, 3 byte. Okay. So the memory you need to specify here. So here we'll be specifying the memory. So the argument to this function is the number of bytes we want. Okay. Now, how much space we want, how much memory we want, a memory which is equivalent to the space required by a node. Okay. How we are implementing a node with the help of a structure. We have created a structure for it. So our node structure is struct node. So we want a space, a memory equivalent to the size of our structure node. That's why we are calling the function size of. Now, as I said you, that depending upon the platform, it keeps on changing. So we do not want to write here a number. For example, I can calculate manually that the size of my structure is 8 bytes. So here I can write 8 simply. I don't want to write here 8. Why? Because our program would be, or is expected to run on different platforms. It may run on Linux, it may run on Windows, it may run on Mac. So depending upon different platform, the memory changes. Different platforms, compiler have different implementation, and on different platform you can have different memory for int, you can have different memory for pointer. Okay, so we don't want to get stuck into that. So what we will be doing, we'll be asking to the system itself, yeah, what is the size? Okay, so what is the size of my node or structure node on your platform? So that can be safely done with the help of size of. So we'll be calling this size of, and what will be asking to this size of function? Okay, what is the size of my structure node on this platform? The platform on which my program is executing. Okay, so it will return us the exact size of our structure node on the underlying platform, whether it is Mac, Linux, or Windows, or whichever compiler. Okay, so depending upon that, it will return us the size of our structure node in terms of bytes. That many bytes will be passed to the malloc function. Okay, to the malloc function. Then this malloc function will request to the operating system Yeah, this program is requesting for this many bytes. Please check whether this many bytes can be allotted or not. The operating system, if available or if it can allocate that many bytes, so it will return the address of the allocated block of the required bytes. If it cannot allocate for any reason, then it will return null value. So there are two possibilities from the malloc function. The malloc would return null or it will return an address. On successful allocation, it will return an address. On unsuccessful allocation, it will return null. Okay. If it returns an address, so it will be returning an address. So it will be accepted into a pointer. By default, the return type of the malloc is void star, pointer to void. The return type of the malloc is pointer to void. Okay. So we need to typecast it. We need to convert it into our pointer. Our pointer is P, this P, and the type of P is what? This. Okay. Type of P is struct star node. Struct struct node star. Struct node star. And that's why while typecasting, we are writing struct node star. Okay, this. And then we are taking it into our pointer P. So our statement becomes P equals to in parentheses struct node star, then malloc, then in parentheses size of, then in parentheses struct node. Okay. So this is how your malloc function would be working. Then we need to check for the value of P. If P is not null, it means that it has an address. So it means that the memory has been successfully allocated. Then only we'll be doing all this stuff. Okay. In the else part, we'll come into the else part if this is not, if this is null. So when P is null, it means that memory is not allocated, and in that case, we'll be simply displaying the message not enough memory or memory is not allocated. Okay. So I hope that your malloc function is clear to you and you have understood the malloc function. Any other query into this? And as said, there is no meaning to execute this code because we are not displaying anything, and we'll be implementing this program in a modular approach. So we'll be having different functions doing different tasks. Insert to insert a node, delete to delete a node, display to display the entire linked list, and so on. Any other query into this? If there is no query, then we can stop here. So can I assume that today's session is understood to you completely, because it is very important. It talks about the fundamentals of linked list. If the fundamentals are clear, then everything about the linked list can be easily understood. If the fundamentals are not clear, then it will be difficult to understand the different aspects of linked list when we talk about the implementation part. So there are no queries, so I'm stopping the recording part, and then I can share the attendance with you, attendance form with you. So our recording is getting stored in Deshmukh Away's Google Drive.